Lesson 4.6, Perform Operations with Complex Numbers. This lesson is going to take a turn from factoring in the last sections. We're asked to first solve each equation. It starts off looking like we're going to extract square roots, just like we did in lesson 4.5. For example A, x squared equals 36. Our x squared term is isolated. What we would do then is take the square root of each side. Remember, the square root cancels with the power, giving us just x. We put that plus or minus out in front, and the square root of 36 is a perfect square. It equals 6. Those are our two solutions. But we run into trouble on the right-hand example. If we say x squared is equal to negative 36, and we try to take the square root of each side, again, we'll get the square root to cancel on the left, but on the right, we can't actually take the square root of negative 36. You can't multiply two numbers and get an answer that's negative. That means this one has no real solution. So then what does this tell us about our x-intercepts for the function? If we were to sketch the graph for example A, our answer was x equals plus or minus 6. That means the function has two x-intercepts. So those would be our p and our q if we were graphing. But on the right, if it says no real solution, that means that quadratic function has no x-intercepts. It's still a parabola, and we could still graph it. It just wouldn't cross the x-axis. Sometimes it's important to carry on past that negative square root. So mathematicians created a symbol or a constant that would alleviate the negative on the inside. And that constant is the letter I. I is a letter that represents the negative part of the square root. The definition for I is equal to the square root of negative 1. How we'll work with it is we'll take out the negative symbol by putting I in front of the radical, almost like a perfect square root that we simplified in lesson 4.5. Once you factor out that negative part in the front, then you simplify the radical using our rules from 4.5. These kinds of answers are called imaginary numbers. Again, imaginary numbers. It means it's not a real solution. The b out in front of the I would represent any coefficient or radical, square root, that's left over with the I symbol. All right, let's see what it means to work with I. You're simply asked to solve each equation. The first example is very similar to the example up above where we said no real solution. We have x squared is equal to negative 13. If we use the extracting square roots rules from 4.5, the first thing we'll do is take the square root of each side. And on the left, it always cancels out, and we have x equals. Remember the rule, always put the plus or minus out in front. But now we have the square root of negative 13. And we can't multiply a number twice and get a negative answer. So ultimately, this is going to be an imaginary solution. What we do to account for that is we circle the negative. And that's almost like our perfect square factor. So it's very similar to the idea of simplifying in 4.5. What we'll do is we'll take that negative and put an I out in front. That indicates that this is going to be an imaginary solution, but it allows us to get rid of the negative on the inside. From here, our goal would be to try and simplify that square root. But if we look at 13, that's actually already simplified. The only factors are 1 and 13. Therefore, our two solutions are plus or minus I square root 13. And we would say that these are two imaginary solutions. That means our graph wouldn't actually cross the x-axis. All right, let's try the next one. We have 2x squared plus 11 equals negative 37. If we want to try to get x squared by itself, we need to move the 2 and the 11 to the other side. But when we think order of operations, we have to do them in the reverse order. The first thing you should do is subtract 11 to move it over. That would give us 2 times x squared. is equal to negative 48. Next, to isolate our x squared term, we have to get rid of the 2. Let's divide. That cancels out the coefficient on the left, and we have x squared isolated. On the right, negative 48 divided by 2 is negative 24. Very similar looking to part A, or example A. If we take the square root of each side, that allows us to eliminate the squared on the left. Again, always remember that plus or minus, and we have the square root of negative 24. The first thing you always want to do is take the negative and put it out in front as I, so that we know we're going to have an imaginary solution. Positive 24 on the inside has perfect square factors. I know it breaks down into 1 times 24, 4 times 6, 9 doesn't go in, 16 doesn't go in, and then we're at 25. So this pair is going to be the pair with the biggest perfect square factor. I'll rewrite this then as plus or minus I, square root 4 times square root 6, and the square root of 4 is 2. So this becomes plus or minus 2 times I, square root 6. Since it's all a product, you can write it in any order. I like to put the I variable, or that I constant, kind of out in front of the square root, so it doesn't look like it's on the inside. All right, let's move on to the next one. Actually, I'm going to have you try this one. Pause the video and see if you can get x by itself. When you think you've simplified completely, press play and we'll see how it went. How did you do? I moved the 33 over and divided by 5 and ended up with x squared is equal to negative 6. Taking the square root of each side, recognizing that we need to put the plus or minus out in front, factor out that negative by putting the I out in front, indicating an imaginary solution, and then noting at the last part the square root of 6 doesn't simplify any further. In all 3 of these examples, we have 2 imaginary solutions. Down below, a complex number. A complex number is formed when part of your number is real and part of it is imaginary. So there are 2 parts in a complex number, either separated by plus or minus. The standard form for a complex number is a plus bi. The a coefficient will represent the real part of the solution, and then the bi coefficient, or the b coefficient with I, is the imaginary part. And you always write the real term first and then add or subtract the bi part of your answer. Simplify and write your answer in standard form of a complex number. Example A, 9 plus the square root of negative 9. Well, 9 would be the a part. That's your real form for your answer. The square root of negative 9, we'd want to factor out the I and get rid of that negative. That would put us at 9 plus I times the square root of 9. The square root of 9 is a perfect square, so we can evaluate that completely. The square root of 9 is 3. We'll keep the first 9 as our a value and 3 times I as our bi value. This is known as a complex number, part real, part imaginary. I know, it sounds so weird. Let's try the next one. Now they kind of flip the order on us, so we'll have to determine what's going on there. Square root negative 25 minus 2. Again, right away when you see the negative on the inside, we know for sure we're going to have an imaginary part to our solution. If we put the I out in front, that makes the 25 positive, and we can simplify that. Minus 2 after, so this is technically our a value. If we evaluate the square root of 25, we get 5i, and then we have that minus 2. But in standard form, the a term has to go first. So we're going to kind of give this a 180. I'm going to flip these 2 around. Notice the 2 is minus 2, so that means the a value is technically negative. This would be negative 2, and since 5i doesn't have anything in front of it, we default it to plus 5i. And there's your answer as a complex number in standard form. Example C, the last example, has us looking at the square root of negative 50. So nothing's being added or subtracted to it. Let's first take care of that negative by putting I out in front. And that makes 50 positive. Numbers that go into 50, let's see, 1 and 50, but that's not a perfect square. 4 doesn't go in evenly. 9 doesn't. Neither does 16. But if we go all the way up to 25, 25 goes into 50 twice. So this would give us I times the square root of 25 times the square root of 2. The square root of 25 is 5, so this would be 5i times the square root of 2. But as a complex number, we have to have it in a plus bi form. So technically we need something added out in front. If there isn't a number out there to begin with, we default our placeholder as 0. So that even makes things more crazy looking. 0 plus 5i radical 2 would be our solution of this complex number in standard form. The main focus for the rest of our lesson will be working with these types of complex numbers. We'll start off with the two basic operations of adding and subtracting. The nice thing about adding and subtracting is we simply combine like terms. The a values will combine with the a values, the bi values combine with the bi values. Let's look at those examples on the right. It says perform the indicated operation. Write your answer in standard form of a complex number. We have 2 minus 3i plus 7 plus 5i. So notice there's a sign in between them for addition. We're just going to add like terms. The 2 would be a like term with the 7. And if we add 2 and 7 together, we literally just get 9. The bi terms, we have negative 3i plus positive 5i. When the terms are like terms, we simply combine the coefficients, kind of like I would be a variable. Negative 3i plus 5i would be positive 2i. And that's really all you have to do when you add or subtract. The trade-off with subtraction, though, is we have to be careful what we're subtracting. So notice there's a subtraction sign in between, so that indicates our operation. But we need to subtract both parts for that second complex number. I recommend you distribute that negative in and rewrite the entire problem. 5 plus 9i minus 1, but then minus that negative I becomes plus I. And sometimes students forget that second part if they don't distribute the negative in. So just something to watch out for. Once you distribute the negative in, and the parentheses don't need to be there, we can combine our like terms. The a's are the 5 and the negative 1. If we combine 5 minus 1, we get positive 4. The i's, we have positive 9i and positive I. Technically, that would be 1i. 9i plus 1i would be 10i. And there's adding and subtracting with these unique complex numbers. And I think that's a pretty good stopping point for right now. Go ahead and look this over before you come to class tomorrow, and we'll complete the back page with multiplying and dividing with complex numbers.